Well, welcome to the last session, and it is my pleasure to introduce a man who needs no introduction, Aleks Owczarek, who's going to talk about self-avoiding walks in a box. Aleks, the floor is yours.
Thank you, Tony. Yes, so again, one had to make a decision about what to speak about, and this sort of has two aspects to it. One is to talk about some work that Chris Bradley and I have done in the past year, which is sort of new work, although it's sort of touching on lots of other people's old work and more recent work. But also I decided that it had some elements to it that were related to the conversations that Richard and I had when I first came to Melbourne about scaling. And also had those with Tony and with Thomas. So that must have been one of the occasions, and you can just see on the part of the whiteboard, there's some exponents. Nu U divided by nu T equals 5 must have been some kind of conversation about scaling arguments. So I had a lot of fun doing that. So this talk contains a little bit of rigorous, touching on some rigorous work, some computer simulation, which I got into with Richard when I came to Melbourne, and scaling arguments. Richard and I spent quite a bit of time talking about them, and with Thomas and with Tony. And a key idea, which I'm not going to go through this sort of arguments itself, but I'll show you the result of them, is about asymptotic matching and how that allows you to match up a so-called crossover scaling form, finite size scaling form, or form in two variables around a critical point, making it consistent with fixed parameter scaling. And it's quite a powerful tool once you understand it. It's nothing greatly mysterious about it once you understand what you're doing. But Richard and I got to that understanding in the 90s. The motivation for this particular problem, from a physical point of view, because we used to talk about physical motivation quite a bit, is about polymers in pores. It's also motivated by some recent work by Bucks and Enzo. There's a self-avoiding walk. We've seen it a few times. So I want to talk about a series of problems, 3 of which have appeared in the literature previously. Under A, we have a self-avoiding walk, unconstrained, and we're going to talk about square lattice self-avoiding walks. We have done a bit today. Unconstrained in any way. There is a dotted line around on there just to say that the self-avoiding walk doesn't care about the dotted line. It just goes in and out. It doesn't care whether it's in a box or not, or in a square. The models C and situations C and D have also been looked at, and we look at those have been studied previously. In C, we see a self-avoiding walk which is constrained to be inside a square, starting at one corner of the square and ending up at the other opposite corner, but staying inside the square. And in D, we have a self-avoiding walk which visits every site, and I think we've had that before today as well, which are known as Hamiltonian Paths. Okay, and so this slide, I think, has appeared in a couple of other people's talks, which is about, and I've got Hamilton 1957, but Stu, I think maybe it's 1954, stand corrected. Instead of connected constant, I'm going to talk about growth constants, which are the nth root of the number of self-avoiding walks. And there's a few people in the audience who have tried to estimate the growth constant of square lattice self-avoiding walks to a large number of decimal places, and people might know a better value now. But that's pretty impressive for an exponential growth rate, that number of decimal places. But the expectation actually is that the number of self-avoiding walks of length n grow in this exponential multiplied by a power law, and we believe we know what the power law is, 43 on 32. We also think we know how the size of a typical self-avoiding walk on the square lattice, in fact on any two-dimensional lattice, will scale as a exponent which is 3/4, which is dependent upon this exponent called mu, which is being predicted to be 3/4 at the high precision by Nathan, in fact, shown to be very likely to be 3/4. Now, there's different ways of describing what that size of a self-avoiding walk is. Often it's called often people measure the end-to-end distance of a self-avoiding walk. Sometimes they measure the radius of gyration to get an idea of the size of a walk. But you could equally think of, well, take a self-avoiding walk and think of the smallest square that you can fit that particular self-avoiding walk in and measure that length. And I'll call that L. And that should scale in exactly the same way because there isn't any other length scale in the problem other than this one length scale. And so it should also go as, that L should also scale as n to the 3/4 in 2 dimensions. Okay, self-avoiding walk crossing a square is a problem with a long and illustrious history. As a problem in combinatorics, there was actually inspired by a paper by the Venerable Donald Knuth, 1976. And Stu and Tony looked at this problem in 1990. Then Neil and Mireille and Ivan and Tony in extensive papers in 2005 looked at this. And there's been some recent work which actually not just about crossing a square, but to do with links that, as I said, Bucks and Enzo, which inspired Chris and I to have a look at the more general problem that we'll look at today. So if you think of walks crossing a square, is a walk crossing a small square of size 5, you should immediately notice that if you consider different walks going from one corner to the other corner, they can be of different length. And in fact, they can be as short as 2L and as big as L squared, I think, plus 2L. So they can be of order L or anywhere in between order L and order L squared. Okay, so you don't have a fixed value of length. Okay. What about the number of them? Well, the number of them, we know something about them. We know that the growth constant for the number of them exists. What is important to notice is this growth constant is defined as the limit L goes to infinity of the number SL to the raised to the power 1 on L squared. And if you think about it a little bit, think that, well, why would it be 1 on L squared? Well, the maximum length kind of walks L squared. So it goes the power that you need to control the exponential growth is 1 on L squared. That value lambda S has been estimated. It's smaller than mu, about 1.7. Okay, and this comes back to a scaling argument. You would expect that the average number of steps goes as L to the 1 on mu. So it's the reciprocal relationship for the walks that are unconstrained. What size box can you fit them in? This is fit the box, what size walks go inside. It's the same understanding of scaling tells you that number n goes as L to the 1 on mu, so L to the 4/3. Okay, Hamiltonian walks. Here's a Hamiltonian walk, a walk, and this you don't really need to worry about whether the walks cross the square or not. But if you visit every vertex of a finite patch of lattice, it's known as Hamiltonian. And again, the number of such walks has a growth constant, which you need to scale as 1 on L squared. Now, all your walks are effectively of size L squared. And that connective constant, or that growth constant, is about 1.47, so smaller than the first two, smaller than lambda s and smaller than mu. And you don't really need to worry about whether the walks start and finish at opposite corners. Now, to sort of connect up these two different types of problem, one where you're worrying about walks of fixed length inside a box of any size, and ones which have a box but of any length, let's introduce a length fugacity. That is a sort of counting variable for the length. You can do that for all of the problems. You can do it for walks that are just in the bulk, that is, there is no bounding box. And if you do that, then you consider the natural partition function for that problem. It's a generating function that in the combinatorial literature, G of W, you sum over all the lengths, okay, and you worry, you concern yourself with what's the behavior of that generating function at different values of beta being going anywhere from minus infinity to plus infinity. Well, what you do know is that this generating function, or this partition function, converges only when beta is negative and smaller than minus log mu. Okay, so log of 2 minus log 2.6. Okay, otherwise the generating function just doesn't converge at all. And in fact, what I haven't written there, because I didn't want to fill up my slides too much, good point, Julianne, is that the generating function has a singularity at beta equals minus log mu, and that gives you gamma, that exponent gamma 43 and 43 and 32. If you calculate the average length, then again it's finite when G is finite, as you would expect when you can calculate it with the derivative of a function which is finite, it's finite, and diverges when G diverges, and it diverges as a simple pole. What about walks crossing a square? So once you confine your self-avoiding walks to be in a box of side L, you can define a partition function, which is a function of L, okay, and it converges for every value of beta, because even though you sum over every value of length, it's possible, you can't really get past L squared, right? So there's actually only a finite number of lengths that you can sum over, and so that the partition function itself is finite when L is finite. But you can define a free energy, which is calculated as the limit of 1 on L squared of the log of the partition function. And you won't be surprised to learn that if you put beta equals 0, effectively you get back your lambda s, which you calculate as that growth constant. Okay, so adding this fugacity expands your problem, makes it a bigger problem and more interesting problem. Now, to cut a long story short, all the work by Mireille and Tony and Ivan and Neil and Stu, well, they showed lots of things, but some of the work they did showed this set of rigorous results with regards to the free energy of walks crossing a square. Firstly, when beta is less than minus log mu, when the actual generating function for self-avoiding walks converges, this free energy is 0. Okay, and it makes sense because you're taking 1 on L, the limit of 1 on L squared log of something, and if that actually ends up converging, dividing by L squared, you end up with 0. So, and that's rigorous. You can show that this free energy exists and is 0 in that region. When beta is larger than log mu, you have bounds, and those bounds depend upon the Hamiltonian value of the growth constant and the growth constant for self-avoiding walks. So log mu h plus beta is smaller than or equal to f s, and you know that the free energy exists. is smaller than or equal to log mu plus beta. So our problem, the one we decided we'd look at, and the only reason, well, there's a couple of reasons. One was that there was a similar problem to do with links, more complicated, that Bucks and Enzo had been looking at. And I thought, oh, well, what's in the literature about just walks in a box without any constraints on their endpoints? Well, couldn't find anything. I thought, oh, well, maybe it's worth just pinning that down and seeing what we can, to see if we can show all the standard things that you can expect from it. So it's not earth-shattering. There's no results here coming out of this that you wouldn't expect, but in fact, it was just that it hadn't been seen before. So we considered self-avoiding walks in a box without any restrictions on endpoints. So the walk can be shorter than 2L. It doesn't have to start and end. It can be a walk of length 1. Okay, it still has the maximum length of L squared, and we'll add in a fugacity to make the problem into this bigger problem. We also considered a problem where you don't worry about translation. The translation is not really relevant. The translation within a box, there's only really L squared maximum places you can move one of the endpoints, and you get any other configuration. And L squared isn't exponential in size, and we're worried really about exponential growth rates of things. So you can actually really only have to worry about walks that are unique up to translation inside a box. And you can prove that. Okay, so there's a walk that we're talking about, walk of any length, starting and ending anywhere inside a box. So that's the physical motivation, as I said before, was walk polymers inside a mesoscopic pore, if you want to sell it to physicists. And we can define a free energy in the same way as we defined a free energy for walks crossing a square, starting at one corner and ending at the other. And you have a similar free energy. And you can calculate, you can also define a free energy, and I put a hat on it for the free energy for walks that up to translation inside a box. Now, you can easily see it's not too hard to show that if the limit with the hat on it, that is up to translation, exists, so does the one with which finish and end anywhere inside the box, including all translations. The two are equivalent. If one exists, if the one without translation exists, the hat version, then the other one exists. What we didn't prove was that it actually does exist. So that's an open problem. But if it does exist, we showed using fairly standard arguments that the following set of inequalities was true. That the free energy for walks in a box without restriction of its endpoints lies in between the walks crossing a square and the free energy for just walks in the bulk plus beta. So the log mu plus beta is larger than or equal to our free energy for walks in a box, F of B, which is greater than or equal to Fs of beta. Now I should state my conjecture that I think that FB and Fs are the same. So we'll leave that as a problem for the audience to prove that they are actually the same. I'm pretty sure that they should be the same. But we didn't have time or ability to do that. So in all generality, here is a picture of what we proved. If that exists, then the dashed dotted blue line, which is our problem, is somewhere in between the orange dashed problem, free energy, and that upper bound. But I think that the blue and the orange lines probably lie on top of each other. I'll get back to one way which you could probably try to pin it down numerically pretty easily if you couldn't prove it rigorously, is to try to find whether lambda b, which is the value of the free energy, the log lambda b is the value of the free energy when beta is 0, is the same as log lambda s. So is lambda s and lambda b the same value? Because of the convexity, presumably you could show that if they're the same at one point, they're the same everywhere. Okay, so that's the small foray into rigor. I sort of chose this talk because of its relationship to scaling arguments and just to demonstrate the power of them. So if we look at the average density, which is just a derivative of the first derivative of the free energy with respect to temperature, with respect to our parameter beta, then because there's a sort of standard scaling at a critical point for the free energy, for any free energy, as beta minus beta c to some exponent 2 minus alpha, that's the sort of standard format. And it's written like 2 minus alpha because the free energy is something which always converges, and alpha is always less than or equal to 1. So 2 minus something which is less than or equal to 1 is also something which is convergent. That the density will scale as beta minus beta c to the 1 minus alpha. Now, here's the sort of scaling scenario in 2 variables. If we go back and consider the finite size situation, where you have a box of finite length L, but make L very large, finite size scaling theory, which is a form of crossover scaling, around the point beta equals beta c, near that critical point, and near L equals infinity, L large, you expect that rho of L will scale as L to some power, which you don't know, multiplied by some scaling function, which depends on a scaling combination. Okay, and that scaling combination is indicative of that average size of the length of the walk inside a box. So that length of the average size of a walk in a box is L to the 1 on nu. And I said to you that for a self-avoiding walk, that the size of the walk has a simple pole in the generating function. And that combination of n and beta minus beta c is kind of what you've got there. And that's the sort of the argument inside the scaling function. So you have this conjectured ansatz format. You can then apply a series of arguments to say that that form has to agree with everything we know about scaling of the quantity of interest, in this case, the density, when the parameter beta is fixed to beta c, fixed to beta less than beta c, and beta larger than beta c. And if you asymptotically match all of this scaling ansatz with those expected fixed beta scaling forms, you can show that Q, the exponent, has to be 1 minus alpha divided by mu. And moreover, you can actually show that alpha has to be a half for everything to be consistent. So in fact, those kinds of arguments that Richard and I talked about ad nauseum are actually quite powerful if you assume that. And so we can write down a density scaling ansatz. This is the density for polymers in 2 dimensions in a box. Goes as L to the minus 2/3, some scaling function, and a combination of beta minus beta c, L to the 4/3. And that is perfectly aligned with the way that the density, hence the density is just the number of steps divided by L squared. The number of steps, the average size of the walk at fixed values of beta less than, equal to, and greater than beta c. Going as a constant times L to the 4/3, and a constant times L squared. And moreover, you need to have that the constants A and C behave in this way. So there's all this sort of a little world of consistency that needs to take place. And you can test any of those things numerically. you can do the same thing for the partition function. You can say the partition function needs to go as some power of L and another scaling function, same scaling combination inside the scaling function, okay? And the same types of scaling arguments tell you that P, this exponent, goes as 2 minus this other exponent in the slew of self-avoiding walk exponents called eta, which is the same as gamma on mu. So that the partition function right at B to C must go as B times L to the 2 minus eta, and eta is predicted to be 5 on 24 in 2 dimensions. So you have this partition function scaling ansatz in the same way as the density scaling ansatz, and you have this fixed beta scenario for of the scaling, which this scaling function matches. Okay, and again, you know how the constants behave as you approach the critical point. So all of those things can therefore be tested. And so Chris and I use the now venerable flat perm algorithm to simulate walks in a box and calculate some data and see how well we can show that all of those things are true. There's some extra things on this plot. I probably should have taken them off, but just look at the top two. The top two are the free energy, finite length free energy, and the density. And you can see that up to some value, which is about 0.97, which is the log of 2.6, minus that, I should say, the free energy is a constant of 0, and so is the density. The free energy behaves in a way which looks like it would, I haven't got the bounds there, but obeys, you would hope, obeys the rigorous bounds that you expect. The bottom two are things I haven't really talked about, so I won't go further. So you can see that the overall generic behavior of the system is as you expect. Moreover, if you look at the critical density at B to C, it behaves exactly as you expect with the L to the minus 2/3. There's our simulation points, and they fit on a straight line. And the scaling function, okay, maybe for large values of the scaling variable, it's not so good, but it does seem to exist a scaling function as you would expect around the critical point. If you look at beta equals beta C, and then you don't just draw a straight line, you try to get an actual value of alpha. I said the scaling arguments tell you that alpha is a half. We get 0.4996 with an error of 8, which certainly encompasses a half. You have to assume mu is 3/4. If you don't assume mu is 3/4, and you use the scaling combination to try to calculate mu, okay, it's not so good, but it's close. Maybe the error bar is clearly twice as large as we thought. If you try to calculate eta, here are 2 different ways of calculating eta. One with so-called just looking at the data raw without with the sort of bulk, the leading term of the scaling behavior, which are the ones that I've written down, and another numerical estimate where we add in some so-called corrections to scaling, which I haven't shown, but if you do that, you usually get a better result. We needed to get a better result here. Weren't happy without corrections to scaling. If you do add in corrections to scaling, then you get 2 minus eta being 1.785, and 43 on 24, which is 2 minus eta, is 1.7916. So none of these exponents are things which are new if calculated is for self-avoiding walks without a box, but we've shown that they're completely consistent with a box. So we've introduced a model of polymers in mesoscopic pores in the context of unrestricted saws and saws crossing a square. We put that model in the sort of the list of problems, and it's sort of a natural physical problem to look at anyway. Okay, we've got some rigorous bounds, we've got some scaling theory, and we've got some Monte Carlo confirmation of those. And those, and I suppose the only part of that this talk doesn't have is some exact results, but Nick and I are working on a slightly different problem with some exact results for walks inside a square as well. This kind of approach to looking at problems in statistical mechanics and combinatorics by using different techniques are ones which I'm very familiar with and enjoyed very much working with Richard and Thomas and Tony for a very long time. So just ending up with some final conjectures or questions. What is the value of lambda b? And those of you with access to perhaps good series analysis might be able to find a good value of lambda b and see if it's as close to lambda s as possible. And those of you who are better at rigorous techniques than us may be able to actually prove that the free energy for walks in a box and crossing a square are actually the same. So I hold out hope that someone with a more subtle grasp on such arguments would be able to do that, which would be very nice. So it's enjoyable to be here this afternoon so much and talk about a problem which I think Richard would have enjoyed very much. So thank you for listening, and I'll take some questions.
Thank you, Alex. Well, as is traditional, we first open questions to people online and then to people in the room. Is anyone online wants to ask a question? No, we seem to have satisfied all the people online. Anyone in the audience? Yeah.
So you said that you ignore the translation.
You can ignore it. Yeah.
Well,
not if they, I mean, if and any quantity would be related to the average over all the configurations, and if you've got a subdominant, that if the things that you calculate, I don't think it can be if the free energies are the same. Certainly the densities won't, because they're derivatives of that. So I highly think that wouldn't be true. But we would actually, the simulations were done I think we worry about the translation in the simulations. I don't think we did. Yeah, it was arbitrary. So
this is all intuitive.
Yep.
Can you prove the bounds in hydrogen?
I don't know if anyone's done that. Walks crossing a cube. Well, I mean,
Neil did it.
I think Neil did, yes. Yeah, right. Neil did it. In dimension, he did. Yeah. There we go.
And if you check the radiator,
We haven't yet.
If I could make a comment and ask a question.
Comment?
The comment is that your first slide, in which you show new self-avoiding walks in 2 dimensions, is old. There's a much more precise result, at least I think two orders of magnitude more accurate in my paper with Jesper Jacobsen in 2015. And the second question, the fact that the free energies for walks in a box and crossing a square are the same, I believe that's almost certainly true. It Am I correct in thinking that the walks you're looking at actually include walks crossing the square?
Yeah, exactly.
So
And because you expect them to be dominated by the ones that are size and square,
yes.
and then you're only worrying, they could start at one end of the box, or they could start and end in the middle of the box, but there's still, there's maybe some multiplicative factor.
I think someone smarter than me could prove it.
We're in the same boat.
With your Monte Carlo work, what size boxes did you use?
What size boxes do we go up to?
The box was 128 by 128.
Yeah.
We can't match that by series. 28.
Still
Further questions? Alex.